Hey team, Editing Maddie here. Just wanted to remind you guys where we stopped the last video and then where we're going with this one. So in part 2 of the first law series, we ended with deriving kind of this first form of the thermodynamics equation, but we noticed that this would be a lot easier if temperature was explicitly in our equation instead of just this change in internal energy form. So that's what we're going to deal with in this video, is getting temperature into this equation, and we're going to see 2 new forms of the first law equation. We have 2 terms in this equation, this change in heating and my change in internal energy, that both are hinting at temperature, but temperature hasn't shown up yet. So something that we're going to do to be able to actually calculate something, right? Like we could calculate the change in temperature of our pot of water, but how in the world do we measure the change in internal energy, right? So what we want to do is relate this term in particular to a change in temperature. And we're going to do that by defining a term called specific heat. Yes, it's specific heat. Past Maddie, don't doubt yourself. Specific heat is this. Specific heat is this term C sub V, and we define it to be dq, that change in heating, with respect to dt, or the derivative of Q with respect to the derivative of temperature. This is some calculus terms here. But we've specifically defined this term for a system where volume is constant. Now, specific heat, fun fact, this is a material property. So water has a specific heat and dirt has a specific heat. And in general, it's just a material issue. You could mess with it a little bit with changing temperature and pressure and things like that. But we're gonna think of this as this is a constant that is experimentally determined that you and I can go Google. There's a table of these values of specific heat values for a variety of materials that you can just find on the internet. So experimentally determined constant. So if this is what CV is, then we could rewrite my dq equals specific heat times dt. Now let's plug this expression in for my dq there. I'm gonna say dq a lot and really want a blizzard. So now we can say that specific heat times the change in temperature. Sorry, it's bad etiquette to talk while looking at the board. Now we can say that specific heat times the change in temperature equals that change in internal energy plus PD alpha. But we defined specific heat to be the value when my volume is constant. So for us to be able to plug this in, d alpha had better be 0, meaning that my change in internal energy is just equal to my specific heat at constant volume times the change in temperature, which gives us a new form of our first law of thermodynamics equation that looks like this, that I really hope is in frame. Huzzah! There is another way to define specific heat, and that's going to be in terms of a system that's at constant pressure instead of constant volume. And through some very similar logic to what we just did, you can get another form of the first law of thermodynamics equation that looks like this. The only difference between this form and the one we just derived is that we're using specific heat at constant pressure times the change in temperature. And then here, alpha is a constant, while pressure is what is changing. There's other ways to write the first law of thermodynamics in equation form, but I think these are gonna be enough for now. So what I wanna do next is use the first law to think about something called a Carnot cycle.
Oh look, editing Maddie's back. We're gonna break this one here, team, and then going into the next video, it's gonna be all about the Carnot cycle and using first law equations to like really understand what's going on in a Carnot engine. So I will see you guys over there. Bye, team.